So you write a rocket of initial mass m0
support there.
a rocket of initial mass m0 expels exhaust at a constant velocity. So this exhaust is expelled at a constant velocity Vr with respect to the nozzle. So this is with respect to the nozzle. The mass depletes at a constant rate r. The mass of the rocket depletes at a constant rate Now this depletion continues till burnout. Till the rocket achieves a burnout. There are certain assumptions to this problem. Assume no atmospheric drag no variation acceleration due to gravity. In the central force problem, if you remember, for normal launching, you launch at certain location, and after the flight is powered, when all fuel is exhausted, at that time the velocity vector is parallel to the surface of the earth. And this is the launching phase, and this is the burnout phase, and this is the powered flight, and then you are having a free flight after point B. So essentially it is something like that. From L to B we are considering the launching of the rocket. So in this problem you are having a rocket with initial mass m0, and this mass, whatever is contained in the rocket, gets depleted because of combustion, and this depletion occurs at constant rate r. Then this depletion continues till the rocket comes to the burnout. No further depletion occurs, combustion stops at burnout. So first, during this period you have to get the velocity v of the rocket as a function of time, and at the burnout what will be the velocity. So burnout velocity will determine the trajectory, right, from your understanding of the central force. And here you have to neglect the atmospheric drag and no variation of g as your rocket moves from L to B. Normally there will be a variation in g because the center distance is changing from the center of the earth. Rocket's distance from the center of the earth is changing, and that should give rise to variation of g, but there is no variation of g, you have to assume. You have to assume there is no atmospheric drag, and here there is a fine point. This VR is with respect to the nozzle, and this nozzle is part of the rocket. So this exhaust velocity VR is actually relative velocity VR is given to you. Now to approach any such problems which involves mass flow, we know that we have to start with the master equation. And the master equation is, to remember it very easily, पहले न्यूटन्स लॉज लिख दीजिए, F equal to m. But remember these laws we had written for fixed mass, no mass flow. Then you add flow forces. Just you remember that m dot O with the positive sign and m dot I with the negative sign. Remember UI, UO and V, these are absolute velocities. This is the absolute velocity of the inlet mass before it is absorbed inside the rocket or the nozzle or the container. And this is the absolute velocity of the exhaust mass after it has left the rocket. V is the absolute velocity, instantaneous velocity of the rocket. And these include the physical forces. Okay. And like we had discussed in the previous class, rocket problems generally involve unsteady flow, because here for the problem at hand there is no inflow of mass, but there is outflow and there is depletion of the rocket mass. Okay, so obviously whatever the mass which is depleting in the rocket, that is obtained as the outflow, right, from conservation of mass. With this, in tandem, there is another equation which is the conservation of mass, m dot I minus m dot O will be m dot, which is the rate of change of mass of the rocket nozzle, whatever of this of the system. Now here, this m dot is depleting at a constant rate, right? And then this is 0. So minus of m dot, since it is depleting, I will write minus r, right? So m dot O will be r. So this is the conservation of mass. This is conservation of momentum, this is conservation linear momentum and conservation of mass. Let me give you through a random question. Can any mass cross a system boundary? System boundary. What is a system boundary? Like I explained, these grade 7 people, individually I call them as systems. So when the class is commencing or is in the process, these are people are seated over here. After some time, they move towards the door and the boundary changes. So system by definition always will involve these 7 people, a fixed mass. System involves fixed mass. So can a mass cross a system boundary? No. By definition, you cannot have mass flow across system boundary. But then in fluid mechanics, you have approach of fixed volume. Control volume. Fixed volume, control volume, not necessarily fixed, it can also be deformable, okay, depending on the problem. But yes, in control volume, which comprises this rocket and this particular boundary, there you can have mass crossing the boundary. So Reynolds transport equation which you have studied, that is actually a link between the system approach and the control volume approach. Okay. So how do you get the deal with quantities which are crossing a particular region in space? So these things are given by this particular equation. Okay, so technically no mass can cross system boundary, but mass can cross regions in space. कंट्रोल वॉल्यूम का जो बाउंड्री है उसको मास क्रॉस कर सकता है, बट सिस्टम बाउंड्री विच कंप्राइजेज अ सेट ऑफ पार्टिकल्स, system by definition the mass is fixed. Okay. So it is like m1, m2, m3, m4, m5, m6, m7, something like that. It will remain the sum of m1 to m7. Okay. Whatever be the boundary, whether they are seated like this or whether they are moving. Okay. Anyway, so here, how will you attack the problem? You will use the master equation in conjunction with the mass conservation. Okay. Now you will also identify other stuff like velocity. What is needed is velocity of the rocket as a function of angle. So you have to bother about this part, what is there in this part. I have already shown weight of the rocket. Sorry?
Lift force.
Lift force. Here, the lift force actually is taken care by the thrust. And thrust, like we have seen in previous class, is generated due to the exchange of masses. Particularly, the outflow of this mass gives a thrust. But the master equation encompasses this plus the exhaust mass. So the thrust becomes somewhat internal to it. But when you look at this equation, like I have said, which part is 0? Mi is 0. M dot O is R. Okay. And you know that this is VR. So U naught minus V is actually VR, and as per the coordinate system chosen, it should be minus VR J. Right? So when you write this summation F, does this make sense? And this you can further write as minus mg j. So to answer your question, this actually is the lift force. ये जब उधर जाएगा तो क्या हो जाएगा? RBR हो जाएगा. And that will be M into so this, the thrust is actually the lift force here. I mean, see, there is a physical difference between the lift force which we had talked about in the previous problem. That is due to the shape of the object moving through the fluid. There will be some lift and there will be some drag. That will be there here as well. Okay, but we are neglecting that. Now, lift as in the rocket's lift, that is generated by the flow of exhaust. There is a nature of the physically there is a difference between these two. ये क्यों हो रहा है? ये लिफ्ट हो रहा है क्योंकि the exhaust gas is moving out, creating a thrust which is accelerating the rocket. And the typical lift and drag, it happens whenever you have flow of bodies inside a fluid medium. Due to the contact force of fluids, you integrate, and the integration results can be resolved along lift and along the drag directions. यहाँ पे भी वो है, okay. But here, because of the symmetry of this particular shape, that lift won't be there. अगर एक shape के वजह से asymmetrical force होगा, then it won't be able to maintain the straight line. Do you understand? Yes. If the rocket is moving upwards and its shape has some sort of asymmetry, that will also create asymmetry of the fluid passing over the things. जैसे ड्यूस बॉल में स्विंग कैसे कराते हैं? हाउ डू यू स्विंग अ ड्यूस बॉल? क्रिकेट खेले हो ना? क्या करते हैं? Make other side. We are creating a asymmetry, right? So the flow of air over the rough surface won't be same as that over the smooth one, right? So the rough will have flow breaking and flow separation, creating a low pressure, and the smooth one, the flow will be largely covering the smooth surface, boundary layer, and then there will be a net force which will laterally shift the ball. Also, I mean, there are also certain conditions also, weather conditions which felicitate swinging action. Long back, हमारे टाइम में बोलते थे इंग्लिश पिच पे स्विंग बहुत अच्छा होता है. I don't know whether it is still true now. That time there used to be matches between counties, English counties. So I mean, I used to see the ball. I mean, used to swing like anything. Indian pitches, man, no. Sorry? No, didn't get it.
लगा
Okay, so what I want to say is that there is no asymmetry of flow. Otherwise, there would have been a lateral lift-like force which would have deviated the rocket from the straight path. So, to the problem now. How will you solve the first part, velocity v of the rocket as a function of time? Before this goes any further, you should also note what is m. This m is what? Mass of the rocket. When it at the start its mass was m naught. Then it starts depleting at the rate r. So this is m naught minus rt. At t equal to 0 it is m naught. Then as t progresses the mass decreases. So which one? It is outlet relative velocity u naught minus v, and that is minus vi. This I have taken in that slide. Obviously lunch didn't go well with you. Okay, now you solve this. dv/dt check this whether you are getting this. Integrate. So let's say when it was initial mass, when the rocket is just about to start with 0 velocity, then the mass is m naught. So at t equal to 0, you can take time t equal to 0 to some time t, or you can just integrate, get a constant of integration and set that to 0. Here putting t is not technically very correct because the variable of integration is t. You should put it t star or something. So better is you integrate, get a constant of integration and solve for it. Using initial conditions. So all of you know how to perform this integration. आता है? Someone is saying yes. All of you are able to integrate this? What is the answer? Plus is that plus or minus? Minus. So C, I think you will get VR ln. Are you getting C? At t equal to 0, what is V? 0. So this is 0 and this is minus VR m naught. So on that side it becomes VR lm naught. So what you get V as a function of time is minus dt. Are you getting this expression? Yes. So how will you get the velocity at burnout? Find me the velocity of the satellite or the rocket. Is there anyone who faced little bit difficulty in this integration, or it was fine? Here there is one thing. Right now, what happens, like as you progress, it may happen that you lose touch with integration and differentiation and these stuffs. You know, but maybe there are some tricks for certain integral forms which you do not know. Now, earlier you had to do the hard way. Open the murderous book of V.S. Grewal. If there is a ODE to solve or something. And being engineers, we are not really very, what should I say, caring about ये आना चाहिए, ये mathematics नहीं जानते, no problem. We look it up and we'll solve it. But now you have tools at your disposal. Not ChatGPT, I mean you have proper tools which is known, goes by the name of symbolic computation. Have you heard about it? So symbolic computation involves the way you are doing in your respective notebooks. Suppose if there is an expression to expand, like a plus b whole square or something, a plus b plus c whole square. How would you do it normally in your notebook? In symbol forms. So whatever result you get, that is in the symbol form. You may end up with some ODE which is non-linear, you want to solve it, okay. Or for that matter, even get to that ODE using some formulation. That too to be done symbolically. So now you have softwares like Mathematica or Maple. There are two different softwares where if you give this in the symbolic form, it will do it in the symbol form itself. These softwares were quite old, but now I think even in MATLAB you can do something using Sims command. Okay. But there is some problem with that. That doesn't have very dexterous applications. It will work for some applications, it may not work for some applications. And now with advancement of Python, you also have some toolbox of Python or some Python libraries where you can do such computations. So this is done. Now you find out the velocity at the burnout. So how do you find velocity at the burnout?
Yes, sir.
You. Amol Palekar. You know who is Amol Palekar? No? You have seen Goldman? But I think the recent ones, not those. There was a Goldman movie long back. So looking at him, I remember that lead role actor. Amol Palekar. You can search. No, don't. Is it matching?
इसके बारे में बात करते हैं इसके बारे में बात करते हैं
Okay, yes, you can search it later. Tell me this answer, velocity at the burnout. At what time it reaches the burnout? At what time burnout occurs? Can you tell me at what time burnout occurs? If you want to find velocity at burnout, you should substitute in this expression that time where burnout is occurring. So obviously the answer you have to first think कि किस time में burnout होगा.
बर्नआउट में वेलोसिटी कांस्टेंट हो जाएगा.
Right, but not relevant at this stage. He is correct. Velocity burnout में constant हो जाएगा. क्यों constant हो जाएगा? Thrust खत्म हो जाएगा. But velocity constant होगा कि नहीं? That also depends on the resulting trajectory. It's good to think. He said velocity will be constant provided if the burnout velocity is root gm by r. तभी circular orbit होगा. और circular orbit में velocity is constant. But if the burnout velocity is such that it is a elliptic orbit, then the subsequent velocity will not be constant. But will be of course governed by energy conservation and momentum conservation. Like you have to always remember burnout के बाद ये दोनों laws are at your service. ठीक है? Both energy conservation and conservation of angular momentum. So at what time burnout occurs? This question remains. So that's very simple, right? M naught minus RT should be equal to the mass of the burnout. So mass at burnout is given. I mentioned it, right? ये कैसा MB है? छोटा MB. So when you replace this at TV, what do you get? Minus G other way what you can think why the speed will not be constant, just another way is that thrust तो खत्म हो गया but weight तो कहीं नहीं गया, that is still doing work. This weight is now the force, the gravitational force. Check if you are getting this. check this answer. So there are two answers. This is answer to 1. And this is answer 2. Done? Any questions? Okay, please write down a open link chain. A open link chain of length L equal to 8 meters. A open link chain of length L equal to 8 meters with mass 48 kg. With mass 48 kg is resting on a horizontal plane. Is resting on a horizontal floor. Have you written that? Now, resting on a rough horizontal floor, right? Rough horizontal floor. When end A is doubled back on itself. When end A is doubled back on itself by a force P. So it is like here you are having a chain, you take one end and you are just doubling it back, means pulling it back. Chain was placed over here, you take one end and you are pulling it back by a force P. So the pink one is the original length of the chain. Once you started with this end A and you start pulling it back. So obviously when you pull it back, there will be friction with the flow. So doubled back on itself by a force P, the coefficient of kinetic friction between the chain and the surface, the coefficient of kinetic friction between the chain and the surface is mu equal to 0.4. The coefficient of kinetic friction between the chain and the surface is mu equal to 0.4. Determine A, the force P as a function of x. Determine the first part A, the force P as a function of x required to pull the chain with a constant velocity. The force P as a function of x required to pull the chain with a constant velocity of 1.5 meters per second. So you have to determine this P as a function of x. Now what is x over here? Let me specify. This is the distance x. So you have to find P as a function of x if you have to move this chain with a constant velocity. You are doubling back at a constant velocity. and the second part B, if the force P is constant, determine the velocity of the chain as a function of x. In the first case, you had constant velocity of the chain. In the second case, P is constant. In the first case, what was written? Force P as a function of x, required to pull the chain with a constant velocity. And in part B, the force P is constant. Then what you have to do? Determine the velocity of the chain as a function of x. So जो constant है, that is of course constant. The other part you have to determine as a function of x. Yes. Have you written the statements? Should I repeat? So now you solve. So we have started chain problem. We have one more class for the tutorial. And if you want little bit more tutorial classes before the midterm, we can do that. Yes. So you want me to slog rather than you slogging. Okay, so master equation remains the same. Okay. Now you have to, there are certain things about chain problems which we will learn only by solving few things. You notice one thing. This part of the chain, this part of the chain is still at rest, and this particular link, this part of the chain is in motion. There are a lot of fine points here which you should pause. इस end को आप P force से खींच रहे हैं. Right? This link is having some velocity. This link here is having some velocity. What is the velocity of this link? This is an open link chain. I mean the links are connected like this. So एक end में if you know the velocity of the link, what will be the velocity? If you know if this is v, what should be the velocity of this link? Why? Because while it is being pulled, it is inextensible, right? So it has to have the same velocity. Okay, so you have agreed this part is in rest, this part is at rest, this part is moving. Now here, if I want to identify a system which gains mass, so which part is gaining mass? Moving part? Moving part is gaining mass. Okay. So we can write our master equation based on this particular boundary. And this boundary mass is always entering it. Do you get this? Mass is always entering this boundary. So, on this particular boundary, here there is link which is entering it, and this particular boundary will be subjected to some physical forces. What are those physical forces? P and friction. It is a horizontal plane. Like I told you, this is the chain. So what you are doing, you are taking this and you are pulling it back. Right? So in this direction, in the plane of the problem, there are only two forces, P and the friction. Is it clear? So let us write that. Also choose a particular coordinate system. So this F is Pi cap minus mu K kinetic friction into the weight of this particular link of the chain. How much is that? X into, but X is not the complete part.
X by 2.
X by 2, very good. Do you agree why it should be X by 2? How can you prove that it should be X by 2? This part, whatever is this length, A, let's say this, the pink part, that is the part which has now become folded and is in motion. So if this is A, this also is A. So A plus A, kitna hua? 2A is equal to X and A is equal to X by 2. Very good. So mu K into rho into X by 2 is the mass. So this completes your summation F, the physical forces. Now in the first part of the question, what is given? Determine the force as a function of X required to pull the chain at a constant velocity. So if it is constant velocity, what will be MA? 0. The system which we have selected, this fixed boundary which we have selected, is gaining mass or is it losing mass? Gaining mass. So is it losing mass? No. So what will be this portion? 0. So what remains is minus m dot I ui minus v. Okay. Now m dot I is the rate at which mass is entering the system. Okay. Now here this is an unsteady problem, mass is entering the system, and what is happening to our system the way we have chosen, इसका mass बढ़ रहा है या घट रहा है? बढ़ रहा है. Right? So if you look at the conservation of mass, m dot I minus m dot O will be equal to m dot. M dot O तो 0 है. So whatever is m dot I is equal to m dot. That means increase rate of change of mass of this particular portion. Whatever is entering at that rate, this mass, this link lengths are increasing. तो ये link length कितना है? x by 2. तो इसका mass कितना हुआ? Rho into x by 2. Rho is the linear mass density. Rho into x by 2 is the mass. What is the rate of change? Rho x dot by 2. What is the mass of the system at hand? ये m क्या है? This is ddt of rho x by 2. So that is rho x dot by 2. And what is x dot? That is the velocity of the chain, that part which is increasing mass, right? Velocity of this part, and all the links are having the same velocity. Now you focus on ui. Ui is the absolute velocity of the inlet mass before it has entered the system. So before it entered the system, this particular link was it at rest. And then it again came to velocity v. There is a impulsive transition. So that's why this is giving rise to a impulse. जो mass पहले 0 पे था, that suddenly now is being added. So this part is going to give you that impulsive or flow force because of addition of the link and causing this link length to increase, the chain length to increase. So when you do it, it is minus m dot is rho x dot by 2, ui is 0, and this is x dot. X dot I, right? X dot. So what you end up with is P minus mu k So what is the force required as a function of x such that the v is constant will be rho v square plus mu k rho g x y. Is it making sense? This is the answer to the first part. Now you try to solve the second part. If the force P is constant, then determine the velocity as a function of x. So if you want to pull the force, this is interesting. If you want to pull the chain with a constant velocity, then you cannot have a constant force. क्यों? फिजिकली कैसे समझोगे? मास इंक्रीज होते जा रहा है. वेरी गुड. मास इंक्रीज होते जा रहा है, तो फोर्स को तो उसी हिसाब से एडजस्ट होना पड़ेगा. So that's why when you want to move the chain, let's say with a constant force, then the velocity will not be constant, obviously. अगर फोर्स को अगर कांस्टेंट रख दे रहे तो मास तो इंक्रीज होते जा रहा है, तो वेलोसिटी तो चेंज होगा. सो विच इज प्रिसाइजली द सेकंड पार्ट ऑफ द प्रॉब्लम. सो व्हाट इज द चेंज इन द मास्टर इक्वेशन? ये तो ठीक है, इसी में क्या चेंज ऐसा आया सेकंड पार्ट में? वेलोसिटी नाउ इज कांस्टेंट और इट इज function of x. That means the chain is accelerating or it is not accelerating? Accelerating. तो ma 0 होगा कि नहीं 0 होगा? 0 नहीं होगा. Very good. So the same thing you have to write. Pi minus mu k rho g x by 2. Now ma, which is the mass portion which we are considering? ये वाला, this portion, where it is gaining mass. इसका mass कितना at any instant of time? Rho into x by 2. And what will be the acceleration? dv. Only this term is added. I removed the subscript k. You can understand that is rho x by 2. Since you have to get the velocity as a function of x, you can always do this manipulation, right? this becomes V dV dx, V dV dx, rho d square by 2. Now you divide this side and this side by x, rho x. So if you divide this by rho x, you will get P by rho x minus mu g by 2. You get V dV dx by 2 plus V square by 2x. What was the need for this? This you can simplify as x square v square. If you do it, you will get x square 2v dv dx plus v square 2x. Now you take 2x square outside. So if you get 2x square outside, you will get v dv dx plus v square by x. There is a by 2, so you do a by 2 and make it this 4x square. So this part becomes 1 by 4x square v dx of x square. After this, you will be able to solve this differential equation and get v as a function of x. So you solve this and let me know in the next class.
Sir, one doubt.
Yes.
Actually, which velocity are we just taking? Are they ui minus v?
Ui minus v. So both of them are absolute velocities. Ui is also absolute, v is also absolute. Ui is the absolute velocity of the inlet mass before it has entered. So this particular link will finally go into this, right? So this is at rest, okay. So you will take ui as 0. Then v is the velocity of this particular system, just a rocket में था. So every link is having this same velocity v towards I cap. One temptation may be there, sir, why are you not taking ui as x dot by 2? Because velocity of this particular upright link, this is not having the same orientation. जो ये है वो भी it is horizontal, this part is also, there is a transition link which is vertical. So it is not having the same orientation. Okay, so that's why we don't take the velocity of that link. जो transition link है, जो upright है, उसका velocity क्या है? A dot. A dot is x dot by 2. But this particular link is like this, not like this. And it is being added finally to the system which is horizontal. So that's why we choose for this particular problems. You have to remember this trick also in further problems, that you choose this trick. This input link before entering this was at rest, absolute rest. So ui हो गया 0.